So last class we were talking about logistic regression, right. So we talked about odds towards the end, we talked about odds and odds ratio, am I right? Right. So now we start looking at, before I get into, so remember the last class we said the logistic regression name is because it is linear in logit function. The logit function is nothing but log of success by failure, that is log of phi of x by 1 minus phi of x, where phi of x itself is 1 by 1 plus e power minus z, where z equals to alpha plus beta x, okay. So that is what we did. So this is what logit function we had, okay, log of phi of x by 1 minus phi of x, that is what I call it as logit function, okay. So the left hand side is non-linear, the right hand side is linear if you look at the left. So the equation is linear in the logit function, okay. So that is why its name is logistic regression, okay. So that is where we ended. And so before I get into delve into deeper, okay, I am going to tell its relation with neural networks, okay. I am going to talk about its relation with a neuron and then move on to the derivation of logistic regression. So let us look at the neuron. So you have this neuron, okay, everybody should be knowing, I do not need to explain how neuron, axon, dendron, dendrite works, okay. So you have, if I want to write a mathematical model of a neuron, you have a set of inputs, let us call it x1, x2 up to xn, these are my inputs, and then these are weighted by weights, right. I am only talking about a single neuron, okay, these are the weights. So there is a weighted inputs coming in, and what this does actually is, if I want to write it mathematically, these weights are summed up, right. So I have summation of W transpose x, if I want to write it, okay, W transpose x 1 cross n into n cross 1, right, that is why it is W transpose x, not Wx, W transpose x, to preserve multiplication, right. And then what do I do? Usually what happens, what is a kind of function for a Hodgkin-Huxley model, some exponentials, sigmoidals, etc., right. So you typically have what do you call it as a activation function, that is the mathematical model, and this is what happens in your, even in your biological neuron, your inputs are weighed, so some of them are high weight, some of them are low depending upon the activation, I mean depending upon the input thing, and then you have a non-linear function happening in your, in your electrochemical gradients formed, etc., right. So that is a non-linear function, and so therefore I have a function of W transpose x, right. So this function typically in the second generation neurons, it is typically a sigmoid function. So now look at this, this is exactly your what, logistic regression. Your output is what? Your output is typically binary, 0 or 1, right. When this function is greater than 0, you have 1, or if it is, so you can associate some greater than some thresholds, you can call it greater than theta, then output is 1, if it is less than theta it is equals to 0, correct, right. And instead of what I call this threshold is added as a bias today, okay. So if it is greater than 0 then it is equals to 1, otherwise it is less than or equal to 0, it is equals to 0. I can add a bias term, and bias is like what, in your neural networks or neurons, the bias is like your previous experiences, right. So this is a mathematical model of a neuron. Look at this, this is exactly like your logistic regression. The first one, especially greater than theta is what, greater than 0.5 you are saying output is 1, less than 0.5 you are saying output is 0, because you are only doing probability of y given x, right. If probability of y given x is greater than 0.5 you say it is the output is 1, and if it is less than 0.5 you have it as 0, and equal to 0.5 is the confusion point, you do not want that, okay. clear, so that you could do a classification. So this logistic regression is actually an exact model of a neuron. Now the question is, what do I want to find out? What are the unknowns here? What is unknown here? Weights, and in our case weights are nothing but thetas, right? Jargons vary, symbols vary, right, but it is the same. Whether you take neural networks you talk about weights, or in logistic regression you talk about parameters, both are one and the same. So if you look at now any neural network, any network you take, any classification problem, each neuron solves what? A logistic regression. Every neuron in your network solves a logistic regression problem, okay, given a cost function, and then finally all this are integrated, I mean propagated, each output is, so this is like your exactly like your neural, so you can understand why the name neural network is, right. So 1940s, so neurons are not known today, the mathematical model of neuron is dates back to 1945, where McCullough and Pitts developed a model called McCullough-Pitts model of a neuron. There they did not have non-linearity, okay, and they had a simple threshold, not like a sigmoid function but a simple threshold. So it worked, but it did not work for even an XOR gate. Everybody knows what is XOR. XOR gate, what is the function? 0 0 0 0 1 1 0 1 1. The problem is 1 1 is 0, it is not intuitive, it is not linearly separable. If one output varies, your output goes to 1, but if two output varies, the output goes to 0, strange. 0 0 is also 0, 1 1 is also 0, so it is not non-linearly separable. So the single neuron cannot solve a non-linear problem, it can only solve a linear separable problem. This was in 1980s, okay. So 1980s neural network came to a halt. For about 1970s, Minsky's paper 1980s, and then up to 1990 2000 there is no significant work. Why? Because of this issue, people gave up neurons and then said this is of no use because it cannot even do an XOR gate classification. How can it do a complex one? Then people figured out that you are only talking about one neuron. What happens in a neuron body? It is a connection of neurons. That is when people started connecting these logistic regressions, okay, and then came out complex classification problem. That is what we call it as multi-layer perceptron. I do not know how many of you heard of this. MLP is actually an arrangement of logistic regression models, multiple classifiers put together, and today that is what we are doing. Today that is the MLP is the the second generation is the foundation for today's third generation neural networks, okay. So we are standing in third generation, but the fundamental is logistic regression, clear. So why is it important, why is it relevant today? Today also mathematically you are only solving logistic regression model, okay. So with that we will go into, we are going to talk about something of this form, z equals to beta naught, which is my bias, and b1 b2 b3 are my weights, okay, and x1 x2 x3 are my inputs. So this is a multivariate problem, right, multiple inputs, output is 0 or 1, the inputs could be discrete or continuous, it does not matter, the only constraint is output should be binary, in this case discrete, and I am solving a binary problem, so the output is 0 or 1, okay. So now I am going to do a, so I am going to generally write it in this fashion, instead of z it is going to be theta transpose x, okay. So z is nothing but my w transpose or theta transpose x. So my function probability of y given x is 1 by 1 plus e power minus z, where z equals to theta transpose x. I am just writing it in a vectorial notation, okay. So this theta could be a vector, theta is a vector here, you have multiple inputs, x is also a vector, like your w transpose x in your neural networks, that is the same thing here. So now we have two parts to this function, we have two parts to this probability of y given x. What is the function when probability of y given x when y equals to 1, and probability of y given x when y equals to 0. When y equals to 1, this is my function 1 by 1 plus e power minus Z, and this is for success. What is failure? Failure is 1 minus success, right. So 1 minus 1 by 1 plus e power minus transpose x. So I can combine it and I have probability of y given y equals to 0 given x is nothing but 1 by 1 plus e power z, and probability of y equals to 1 given x equals to. Now the question is, how do I put them together? You have two objectives or two functions, one for success, another for failure. How do I put them together? So the one is for success, the other one is for failure. How do I combine them together is the question. Okay. So there is an intelligent way to combine them. Okay. So this is what I have. What is my prediction? My prediction function is 1 by 1 plus e power minus z, right. That is my function used to predict the probability. So I write it as y hat, always hat stands for prediction, y hat is my prediction, y hat to the power y into 1 minus y hat to the power 1 minus y. So suppose in this function if y equals to 1, what happens? Which function becomes active? First function becomes active. That is what you want when y is equals to 1. When y equals to 0, which function becomes active? This part, this is minus, right, this part, this is what you want when you want y equal to 0. So what did I do? I have intelligently combined the function for both output 1 and output 0. Now where will I use it? I will come back. Okay, I have combined them, I will use it elsewhere. Okay, why did I do this? You will get to know. So the way to combine this is very simple, y hat to the power y into 1 minus y hat to the power 1 minus y. So suppose y equals to 1, the first part becomes active, which is what is required, and if y equal to 0, the second part becomes active. Clear? So now we have combined the both success and failure, we have combined into a single function. Okay. Now what is next step is to estimate the parameters. Okay, we have been delaying so far, but the key idea is to estimate the parameters. How do I do it? We can start talking about simple mean squared error. Remember, that is what we did in your linear regression. What did we do? We minimize the mean squared error, 1 over n summation y minus y hat the whole square. And what is y hat? We know it is nothing but 1 by 1 plus e power minus z. Okay, we could have done that, but remember my output is going to be what? In this case it is not going to be continuous, in this case it is going to be either 1 or 0. When there is an error, what is the error value? 1, and if you square it, it is 1 squared. When there is no error, it is going to be 0 squared. So what are we going to do? We are going to have 1 square plus 1 square plus 1 square plus 0 square plus 0 square plus 0 square, something like that. So the function is not going to be smooth, it is a non-smooth function. I have drawn this here. If you just use cost function, which is my MSC, the function is not going to be smooth. Why? You will have continuously zeros and then suddenly you will have continuously ones, then zeros, etc. So this is going to be a bumpy function, it is not going to be a smooth function. So you cannot obtain a global minima easily, you will have many local minimas, because MSC is going to be just a summation of ones and zeros, it is not going to be a smooth function. Okay, you will have many local minimas along with the global minima. Okay, so you do not want this kind of function. Okay, you do not want to use mean squared error to minimize. Okay, you do not want to use mean squared error function at all. Okay, that is where the issue, that is where the problem is, because if you use mean squared, you kind of get this graph where the function is bumpy function, cost versus error, the error keeps on reducing and so all of a sudden it will be addition of ones, then addition of zeros, then addition of ones, etc. So it is going to be crazy function. Okay, ideally what do I need a function to be? I want a function such that when there is no error my cost is 0, when there is a error the cost is very high, okay. You just do not want the cost to be 1, because addition of ones it is only making a small increment, whereas you penalize the error very highly. If it is no error you give a 0 cost, if it is an error you give a very high cost. You want a different objective function, you do not want this mean square objective function, because mean square error is simply addition of zeros and ones. If you take a regression problem it may be a huge number, error may be huge and then square of the error will be very high. In this case the error is only 1, even if you make an error it is only 1 squared, which is just 1, right. So that is why you do not want this objective function, you want to go with a different objective function, and that is what we are going to derive, okay. So remember we have combined both of them together. I told you 1 and 0 we have combined together as y hat to the power y into 1 minus y hat to the power 1 minus y. This is my probability of y given x for both, for y equals to 1 and y equals to 0. This is my combined function, this is my combined function, clear. Now what am I going to do? I am going to take logarithm on both the sides. What will happen if I take logarithm on logarithm? I will have y ln y hat plus 1 minus y ln 1 minus ln 1 minus y hat. This is ln of probability of y given x. I am taking logarithm function on both the sides, so this is what I have, clear. Everybody clear with that? How did I get it? Simple ln function, okay. Then I am going to take negative of this, I am going to take negative of this. What is ln 0? In your range 0 to 1 the ln function is entirely negative, okay. Ln 0 is minus infinity, ln 1 is 0, so the range of 0 to 1 the entire ln function is actually negative. The ln function in the range of 0 to 1 is like minus infinity to, this is how you have ln 0, ln of ln 1, ln 0, this is all in the negative axis. So to keep it positive I take a negative sign. So what will I have? I have multiplying throughout, what do I have? Minus 1 ln y hat minus 1 minus y ln 1 minus y hat. Clear? Is this clear? Now I am going to take this as cost function. I want to minimize this cost function. I will tell you why this minimizing cost function is making sense. I will derive the graph, I will show you the graphs, but I am going to minimize this cost function. I will show you why this is valid, okay. Everybody agreed? So I call this as, this function as, this is nothing but negative, okay, and this function is also called as cross entropy function. Have you heard of this name, cross entropy? If you go through neural networks or machine learning, the objective function for classification is cross entropy, that is how much probability that it will be classified erroneously. So this is what is cross entropy function. So this is actually a cross entropy function, and people also call it as log likelihood function, okay, log likelihood function, because you take this log how much y hat is close to y, the ln of y hat how much is it close to y, that is why it is a log likelihood function. These are very important functions, objective functions. You only know minimizing mean squared error so far. Now we have learned one more function which is cross entropy function or log likelihood function. And today's neural networks or machine learning algorithms, if you go, the most popular objective function, two most popular objective function is minimizing mean squared error, the other one is cross entropy. Okay, they may do weighted mean square, but in classification problem the standard objective function is cross entropy function, and the cross entropy function is nothing but y log y hat minus y log y hat minus 1 minus y log ln 1 minus y hat. This is what we derived actually. How did this function come also I showed you, like starting from the sigmoidal function. Okay, so this is my cross entropy function. Okay, so why does this make sense? I will show you graphically. Okay, let us draw a graph of log. Okay, let us draw a graph of log z. Okay, so this is my x value. Okay, so this is my z value, I will say z, which is nothing but z is nothing but theta transpose x. So this is my z value. When z value is 1, log z equals to log 1 equals to 0. Okay, and when z equals to 0, log 0 equals to minus infinity. Okay, so this is my graph of log of z. Now let us plot what is minus log z. Minus log z is going to be what? Just the opposite, right? Mirror image. Negative is actually a mirror image. So this is minus log z. Okay, now your objective function is what? Your objective function is minus y ln y hat minus 1 minus y ln, agreed. Now let us say, let us consider y equals to 1. When y equals to 1, what happens? The second part goes to 0, second part goes to 0, right. What do I have? I have objective function is what? Minus ln y hat. What is the objective function? This is my objective function, clear. Minus ln y hat is nothing but z only, right, 1 by 1 plus e power minus theta transpose x, that is what I have written it as z. So this is my objective function when y equals to 1, clear. Any questions graphically? Now your error should be 0 when y hat equals to 1. Look at this, when y hat equals to 1, what is the function of minus log of y hat? Minus log 0, sorry, minus log 1, 0, right. When y hat equals to 1, truth is y equals to 1, I have considered a case where y equals to 1. When y equals to 1, what is the objective function? Minus ln y hat, minus ln y hat. When y hat equals to 1, what is the value? Y hat equals to 1 minus ln y hat equals to 0. So error is, cost is 0, you have minimized the cost. Now when y hat equals to 0, what is the output? Minus ln 0, minus ln 0, infinity. You have a very high error. This is what you want. When there is no error, your cost is 0. When there is an error, your cost is infinity. So that you want to minimize this function. If you minimize this function, that means you have predicted got the parameters, right. So this is case where when y equals to 1. Okay. Now assume a case where y equals to 0. When y equals to 0, what is my cost function again? Minus y ln y hat minus 1 minus y ln 1 minus y hat. So when y equals to 0, what happens? This goes to 0. So what is my then output? Minus my objective function. My objective function is minus ln 1 minus y hat, clear. And this is the graph, the second part, this is the graph of minus ln 1 minus y hat. Okay. So my objective is minus. So when y hat equals to 0, what is my output? Minus ln 1 minus 0. What is my output? Minus ln 1, cost is 0. when y hat equals to 1 you are predicting it wrongly. Notice the truth is 0, you are predicting wrongly. What is my cost? Minus ln 1 minus 1, that is minus ln 0, which is infinity. So in both the cases, if you predict wrong, the cost is very high, and if you predict correct, your cost is 0. So now what is my objective function? My objective function is j, if you want to call it, it is nothing but minus 1 minus y ln, sorry minus y ln y hat minus 1 minus y ln 1 minus y hat, and this shortly written as minus ln of y comma y hat. This is my cross entropy function. Or likelihood function. Clear? Make sense? So this is my new objective function. You wouldn't have heard or read about this objective function at all, you would only know mean squared error, that is only for prediction problems, meaning continuous outputs. This is for classification problem, that is predicting discrete outputs. Clear?